12.1, exploring solids. A solid is basically a three-dimensional figure. The types of solids we're focusing on in 12.1 is a polyhedron. That's a solid that is bounded by polygons. It's made of polygons. As you can see here, we have a polyhedron, and it's made up of two triangles. Those are going to be the bases actually in this polyhedron, and then three rectangular sides. Okay, so the faces are the polygons, and the edges are where the polygons meet. The edges are where the polygons meet, and the vertex is where edges meet. Now there are different types of solids. There is a pyramid, which has a base, and then from the points on the base, the edges come up to meet at a point. So the faces, lateral faces, are going to be all triangles basically. There's a prism, which has two congruent bases. So this has two bases. Those bases are both congruent and parallel. Okay, so notice these rectangles cannot be bases because they're not parallel. So they are congruent and parallel. That's a symbol for parallel. Pyramid just has one base. These are both polyhedron because they are made up of polygons, where a sphere, cylinder, and cone, these are not polyhedrons because of their rounded circular bases. Okay, and the sphere doesn't even have a base. All right, decide whether a solid is a polyhedron. If so, count the number of faces, vertices, and edges. This first one is a polyhedron. It's made up of a pentagon and triangles. So the faces, vertices, and I'm going to extend down here a little bit ways, and edges. Okay, the number of faces, when you're counting these, I usually start with like a base. So the base is a pentagon, so that's one pentagon. If you need to, write it out, one pentagon. And then a pentagon has 5 sides. Each side is going to have a triangle off of it. So 5 triangles. You know, list that out if you need to, so that's 6 faces total. Vertices, okay, the one pentagon is going to have 5 corners, and the one on top, so that's a total of 6 vertices. And the number of edges, there's going to be 5 edges on just the pentagon part, and then up from each corner of the pentagon we have another edge. So there's 5 vertices. That's going to make a total of 10 edges. Over here on this polygon we have 2 square bases and 4 rectangles. So if we do faces, vertices, and edges over here, so 2 squares plus 4 rectangles, that's a total of 6 faces. Vertices, there's going to be 4 corners on the bottom, and then they meet in 4 corners on top, so that's a total of 8. And edges, I'm going to start with the base. There's 4 on the base on the bottom half and 4 edges on the top half, and plus we have the segments connecting the bases. Don't forget about those. So we have a total of 4, another 4, and another 4, so 4 times 3, or 12. Now, there is a theorem named after a mathematician, Euler, so we call it Euler's theorem. um, what it says that the faces plus vertices equals the edges plus 2. So we can verify this to make sure we did this right by taking 6 plus 6, and does that equal 10 plus 2? Faces plus vertices, edges plus 2. And it does, that works. And you can test it for any polyhedron. So 6 plus 8, does that equal edges plus 2? That's 14. That's 14. It works. And we're going to actually use this later on in the section. Which letters are polyhedrons? First off, let's identify a polyhedron. Since this has a rounded edge, okay, it's not a polyhedron. Same thing here. Rounded edge, not a polyhedron. Next, for it to be regular, the faces all need to be congruent. And faces need to be congruent regular polygons. So remember, regular polygon, all the angles are congruent in the polygon, and the side lengths are all the same. So if you look at this F, we have a square here, a rectangle there, an F shape here. This is not regular. It's not a regular polyhedron. This one gets close, but once again we have a square here, rectangle, so it's not either, not regular. Now, as far as convex, the definition for a convex, remember it's convex, or the other word, or concave is the other option. I don't mean these are the same, but they're different, right? Convex or the polyhedron will be concave. Has to be one of the two. So concave is it went in. So if you pick 2 points, and if that line between those 2 points is outside of the polyhedron, that means it's going to be concave. Okay, so same thing here. I could pick this point and this point, and since the line lies outside right there, it's concave. But any 2 points you pick, it doesn't even have to be an endpoint. Any 2 points, if you draw that line and that line is all the way inside, that's going to be convex. So that's a convex polyhedron. This is a concave polyhedron. Cross sections in a poly. For cross section is just where a plane would intersect the figure. So I always think about it. If I sliced it with a knife, what shape would be left? So oftentimes when you talk about the cross sections of a cone, you can have a few different things happen. If I cut it here, it's going to be an ellipse, or if I cut it parallel to the base, it actually turns out to be a circle. Okay, an ellipse is kind of just a stretched out circle. If I cut it parallel to one of the sides, it's a parabola. That's kind of that like y equals x squared graph. If you remember graphing those, that's called a parabola. It's kind of steep, but more of a U rounded shape on bottom. And this is a hyperbola, which is actually more kind of like a V shape. It's kind of more pointed. It's still round, but it follows kind of a straight line. It pretty much is a straight line after that, where this is it's still kind of rounded. And so here's the spelling of those things. Feel free to check out this website to see some other geometric shapes. It's kind of interesting. We'll move on, and we'll go to this last problem. Okay, this is a thinking problem, so it's definitely not easy, but we have to think. First off, we know it has 10 faces. So 4 triangles, 1 square, 4 hexagons, and 1 octagon. We're going to use that to figure out how many edges there are. If you look back to one of these earlier questions, this one, okay? We had 1 pentagon and 5 triangles. If I just told you this, could you figure out how many edges there were? And notice, an edge is always shared by 2 polygons. So if I know, like a triangle here, triangle is going to have 3 edges. It's got 3 edges, but notice it, each triangle, they're overlapping. So this edge is shared by 2 triangles. So if we figure out a pentagon has 5 edges and 5 triangles, 5 times 3 would have 15 edges. We don't have 20 edges, but since each edge is shared by 2 polygons, we have to divide that by 2 to get 10 edges. If you look at how many edges we had 10. So we're going to do the same thing in example 4 to figure out how many edges there are. Okay, so we know there's 10 faces. We're going to figure out how many edges there are next. So 4 times 3 tells me the number of edges on the triangles, plus 1 times 4 edges of the square, plus 4 times 6 edges on a hexagon, plus 1 times 8 edges on an octagon. But the problem with this is we double counted, right? Somewhere along the way, one of the edges on a triangle is going to share with one of these other shapes, or another triangle even. So I have to take that number and divide it by 2. So 12 edges for the triangles, plus 4 edges on the square, plus 24 edges of the hexagons, plus 8 edges on the octagon. Divide that by 2. Add these together, we get 16, 40, 48. 48 divided by 2, we have 24 edges. So now, how do we figure out how many vertices there are? We get to use Euler's theorem, faces plus vertices equals edges plus 2. Plug in 10 and 24, and we should be able to solve this. So we have to have 16 vertices. So notice, if someone gave us these shapes and told us to make something out of them, figuring out 16 vertices and 24 edges would be very helpful. There's your homework assignment. Till then, penguin.